Okay, let's talk of the reverse of what we talked about before. So far, we talked about what happens to light when it moves from one medium where n1 is small to a medium where n2 is larger. And we have observed that in that case, light is going to bend with the angle of refraction, the angle of transmission or refraction being smaller than the angle of incidence. That's for this case. Now, what about if n1 is actually larger than n2? Recall Snell's law. If n1 is larger than n2, that means theta 1 is smaller than theta 2. That's what we have. So instead of the angle of transmission being smaller than the angle of incidence, the angle of transmission is going to be larger than the angle of incidence. So the beam is going to bend away from the normal as opposed to towards the normal. So this is, for example, my n1 being the larger of the two. And then, as we move in the second medium, I have a larger theta sub 2. Okay, now, as you consider that theta 2 is going to become larger. Okay, let's go to the simulation in this case. Okay, let's see. Okay, here we go. So I'm going to change the roles. So I'm going to start with n1 being 1.5 and n2 being 1. Oops. Okay, let me move the light source to the middle. Okay, you notice here that the angle of incidence is smaller than the angle of refraction. Now, as I increase the angle of incidence, the angle of refraction is going to obviously increase. Okay? And there we go. Notice that there is one point where suddenly there is no more light going into other medium. Now, theta sub 2 is large, and then it becomes equal to 90 degrees. At 90 degrees, I don't have light going in here anymore. And in this particular simulation, they stopped from showing it. All the light is reflected. So we call that angle the critical angle. It is the angle beyond which no light is going to move into the second medium. So if I increase my angle, no more light going into that medium. It goes into the medium only if theta is smaller than that critical angle. Okay? Now, how do we calculate that angle? We just plug in 90 degrees for theta sub 2. When we do that, then my equation becomes n1 sine of theta 1 is equal to n2 sine of 90 degrees, but sine of 90 degrees is equal to 1. So that means sine of theta 1 is equal to n2 over n1, and solving for theta 1, it is equal sine minus 1 of n2 over n1. That particular angle, we call it critical angle, and usually we use the C label for it. So the critical angle is the angle of incidence for which the angle of refraction is 90 degrees. Beyond that critical angle, no light is going to emerge into the second medium. Graphically here, you see this purplish colored beam is the beam where the angle of incidence is theta sub c. theta sub 2 is just 90 degrees. The blue beam, that's a beam where the angle of incidence is larger than theta sub c, then no light is going to come out. And we say that we have total internal reflection. When do we have total internal reflection? Whenever the angle of incidence is larger than the critical angle. That we can calculate using that relationship. Inverse sine of n2 over n1. Okay? What are implications of this? Let's try to ask this question first. Now, can the person standing on the edge of the pool be prevented from seeing the light by total internal reflection? Can the angle of the light being reflected off that coin be such that the person is not going to be able to see it? Okay. Now, to answer that, let me go back to a simulation that we saw before. Okay, now this is the person observing, and this is our object. And you notice, no matter how I place my object, even when I increase the angles, look at that. So there is a lot of light from that point that's totally internally reflected. But then because light is shining at all directions, I mean light is being reflected at all directions, there's still going to be beams that are going to make it to the viewer, no matter where I go. Okay? So the answer is no. Okay? Now, let's look at this other picture. Now, this is one of you after becoming a doctor. That's another one after becoming a surgeon. I'm not sure if one of you is interested in becoming a clown or a comedian, but we have a clown there. And we have actually a young kid there. One of these people is actually famous in the pictures. Okay, now what does the question say? We have a coin at the bottom of a container, and we start adding water. And the question is, as we pour more water into the bucket, what will happen to the number of people who can see the ball? Okay, or the coin, or whatever it is. Is it going to increase, be the same, or decrease? Okay, we can go back to the same simulation that we had. What does it mean to say increase the amount of water? Like here, that's a little bit of water. And look at the rays. How are they being refracted? So it's going to be difficult for a person here to be able to see that sphere. But then as we go deeper, look at the way the light is coming off. Okay, of course what I need to do is, okay, you see more and more light coming in down here. So the answer is, the deeper you go, let me show it more here, the more people are going to be able to see it. Okay, let me show it some other way with another simulation. Okay. Again, doing the same thing. So this is at this particular depth. You see, as it is shallow, you have less light coming out in this side. As we go deeper, we have light being refracted into positions where more people can see the object. Okay. See more of it and more of it. Okay. So the number of people is going to increase. Okay. Another thing I would like to show you before we get out of this. Actually, let's close this. It's not this simulation. Let's go back to here. Okay, this is, so we have a light beam and the index of refraction N1 of medium 1 is higher than N2 like we had before. And look, what does this mean? I wanted to show you the simulation here to illustrate that science or physics or nature is a little bit more complicated than just the simple case we just discussed. So actually you notice here there is a slight penetration of the wave into the new medium. It's not a clear cut, no penetration at all. And this is for an angle of incidence 45 degrees, larger than the critical angle, which is in this case 41.8 degrees. Okay. Now, of course, I was showing you here both beams. That's the interference between the reflected and the incident. Okay, you can have a bigger view of that. Okay. And you see how the traveling wave is. And this is the reflecting, the incident wave by itself, the reflected wave by itself, and the actual interference. Okay. Another thing that I would like to show you now, going back to the simulation, let's go back to 1 here and, oops, let's see, let's say 1.5 approximately. I could have just reset it. Okay, 1.33. Okay, we talked about the apparent depth. It's going to be less because we have a higher index of refraction. Let's reverse the roles a little bit. What I'm going to do is I'm going to take, when it's going to allow me, again, okay, and I'm going to move the eyes below. Okay, and right now here what we are going to have is two things. This is my object, and we added another object, this one here, the hand. Now as we play, you look there. Okay, there is a point beyond which we don't see the object that's below the reflected image, and that's because most of the light is going to be transmitted. Okay. Now, but if you pay attention to the fish, like you expect it, when you look at the image of that fish, it's going to look inverted. And that's what we see. Now the hand, it's going to look like it is further out, but you don't see it inverted. You see it distorted. Okay? The fish, you notice there, you don't see it distorted. Just to make sure that we get that point, we see that point carefully, I'm going to use the other simulation that has the sphere to look at it again. So I'm going to try to do the same thing. Come on. Okay, so look here at the case of the sphere. This is my object that is underwater, and we see its image. Notice that there is no distortion because we are looking at this actual object. We are in the same medium. Okay, so we are looking at reflected light. That's what's coming into the eye. And that does not result in the distortion. You have a flat surface. Now, that's like a flat mirror. That's the image that we see. However, the image that's coming from refracted light, this is the image of the red sphere, we see it looking like it's further out, since we are going from a high N to a low N here, but then it is looking distorted as well. The larger the angle, the bigger the distortion. Okay? Okay, and one last thing to mention when talking about total internal reflection. Most of you, as you are watching this video, you are watching it using an internet connection, and you know that the faster the internet connection is going to come to your house if your neighborhood is being connected to the internet via fiber optics. Now, fiber optics are going to transmit signals through tubes of glass, essentially, tubes of translucid material. Now, these fiber optics, so we have a translucid material here that's bordered by the orangish color, and then we shine the signal in the form of light, and as the light is going to hit the kinks in the wire and the fiber, we want it to reflect such that none of that light intensity is going to come out. If it comes out, you are going to lose most of the signal and you'll get nothing at the output. So we are relying here on total internal reflection to get the beam to travel without much loss. Now, so it is important that the angles that is going to hit the surface is going to always be larger than the critical angle. Now, what's going to set what critical angle do we have is the difference between the medium of the translucid material and what we call the cladding, the medium that we use to surround that translucid material. It is important that we use cladding because if we don't, then the behavior of the fiber is going to depend on what kind of medium we use the fiber in and whatever environment we have. For example, temperature changes, you put it in water, for example, in oceans or in air, so that's going to change things and make things unworkable. But with the cladding, you can set it up once and for all, and you can set it up for the particular frequency of light that you are going to send in, be sending, and you'd like to make sure that the index of refraction of the cladding is less than the index of refraction of the translucid material of the fiber.